Retrofitting the static glass tower, a climate-responsive secondary skin for Suzhou Daily Group headquarters. This project investigates the retrofit of Suzhou Daily Group headquarters, a curved high-rise office tower located in Moonbay, Suzhou. The existing building is visually strong, with a continuous glass curtain wall and clear urban identity, but environmentally it behaves as a static envelope in a hot, humid climate. My proposal doesn't replace the whole facade. Instead, it adds a lightweight, climate-responsive secondary skin of vertical fins. The aim is to reduce solar gain, improve comfort, maintain views, and extend the life cycle of the existing facade through a lower carbon retrofit strategy. This page introduces the site and the environmental problem. The tower is located in Moonbay, within a dense lakefront business district, surrounded by roads, hard surfaces, open sky exposure, and nearby high-rise buildings. The existing facade is a curved glass curtain wall with a high window-to-wall ratio. This gives the building good daylight and panoramic views, but it also increases exposure to solar radiation, glare, and heat gain. The key argument here is that the building already has a strong architectural base for retrofit. The structure, facade rhythm, and curved geometry can be retained, while environmental performance can be improved through an added external shading layer. This page identifies the existing facade typology. Based on visual inspection, the tower appears to use a unitized or semi-unitized curtain wall system, with repeated glazed modules, aluminum mullions, horizontal transoms, opaque spandrel zones, and small operable window sections. The facade system is visually efficient and modular, but it has limited external solar control. The circular floor plan also places occupied office spaces directly along the glazed perimeter, so the performance of the facade strongly affects indoor comfort. The main diagnosis is that the facade works well as a transparent visual envelope, but not as a responsive environmental filter. This creates the opportunity to retain the existing system and improve it through a secondary external layer. This page presents the environmental simulation of the existing facade. I used a simplified Rhino and Ladybug model to test direct sun hours and solar radiation across different seasons, orientations, and floor levels. The results show that the south and southwest facade zones receive the highest solar exposure. East and west zones are also important because low-angle morning and afternoon sun can create glare. The north facade receives lower solar radiation and can therefore remain more open. The key conclusion is that a uniform retrofit would not be appropriate. The shading response should be orientation-based, with denser protection on high exposure zones and lighter intervention where views and daylight can be preserved. This page connects the facade problem to the interior condition. From the site visit photographs, the building has large glazed areas, double height spaces, and occupied zones directly beside the curtain wall. These spaces benefit from daylight and views, but they are also exposed to glare, radiant heat gain, and thermal discomfort. The operable window areas appear small compared with the total glazed surface, so passive ventilation is limited. The plan diagram shows that the comfort risk is concentrated around the glazed perimeter. The existing facade performs visually as an open office envelope, but environmentally it creates a continuous risk zone of glare, overheating, and mechanical cooling dependency. This page expands the analysis from the building interior to the urban and life cycle scale. At ground level, the tower base, hard landscape, roads, and reflective glazing can affect pedestrian comfort through wind acceleration, glare, and heat buildup. The life cycle argument is also important. A full curtain wall replacement would create significant embodied carbon through demolition, disposal, new glass, new aluminium, transport, and installation. Therefore, the retrofit strategy should avoid unnecessary demolition. The more sustainable approach is to retain the existing facade structure where possible and improve performance through selective, reversible external upgrades. This page introduces the design proposal. The strategy is to retain the existing curved curtain wall and add a lightweight external layer of vertical fins. The fins follow the geometry and rhythm of the existing facade, so the original tower identity is not erased. Their depth, density, and angle change according to the orientation. South and southwest zones receive deeper and denser shading. East and west zones use angled fins for lower angle glare, and north-facing zones remain more open. A key addition is that selected operable fins can be inserted between unitized curtain wall modules to support additional ventilation. The proposal, therefore, improves solar control, daylight quality, ventilation potential, and life cycle performance without fully replacing the building envelope. This page explains the material and circularity logic. The retrofit uses recycled aluminum fins, powder-coated aluminum brackets, stainless steel fixings, EPDM or thermal brake pads, and selective low-E or solar control film upgrades only were required. The central idea is to use low-carbon, modular, and reversible components. Instead of demolishing the whole curtain wall, the existing slab edge, mullions, glazing, and facade rhythm are retained as much as possible. The exploded axonometric shows the assembly logic: existing slab edge, existing curtain wall mullion, new support bracket, secondary rail, operable vertical fin, ventilation panel, and maintenance access zone. This makes the proposal more technically believable and support future replacement, repair, and disassembly. This page shows the architectural impact of the retrofit. The before image shows the existing static glass tower, while the after image shows the same building upgraded with a vertical fin secondary skin. The important point is that the building is not redesigned from scratch. The curved tower form, podium, facade rhythm, glass identity are still visible. The new fins add depth, shadow, and environmental control while still keeping the original architecture legible. This visual summarizes the project intention, transforming the tower from a reflective glass envelope into a more climate-responsive facade system. This page compares the environmental performance before and after retrofit. The main simulation evidence is the solar radiation comparison. The existing facade shows high solar exposure on the curved glazed surface. In the retrofit condition, the vertical fin layer filters and redistributes incident radiation before it reaches the primary glazing. This reduces direct solar gain on key facade zones. The table also summarizes broader expected improvements: reduced glare, more controlled daylight, improved ventilation potential, lower cooling demand, reduced embodied carbon compared with full replacement, and easier maintenance through modular components. This is an early stage performance comparison, not a final engineering prediction, but it demonstrates that the retrofit strategy has a measurable environmental logic. This page translates the proposal into technical drawings. It shows the 1 to 20 facade section, a close-up render of the retrofit facade, and elevation drawings showing the vertical fin rhythm. The section explains how the existing curtain wall remains the primary enclosure, while the new vertical fin system is added externally as a secondary environmental layer. The important components are the existing slab, existing curtain wall frame, insulated glazing, support bracket, vertical fin, and ventilation path. This page is important because it shows that the proposal is not only conceptual, it has a tectonic and construction logic that could be developed into a real retrofit system. This page focuses on the key junction and environmental detail. The drawings show the relationship between enclosure, ventilation, operable fins, and assembly. The first section shows the typical facade junction and how the operable fin layers sits outside the existing curtain wall. The second detail shows how air can move through the additional fin or ventilation module, supporting improved ventilation and reducing heat buildup. The key technical idea is that the facade becomes a layered system. Existing enclosure, ventilated cavity, operable external fin, and bracket support. This improves solar control and ventilation while keeping the intervention reversible and relatively low impact. This page presents the retrofit at facade scale. The close-up views shows how the vertical fins change the experience of the building by adding depth, shadow, and a stronger environmental rhythm. The fins are designed to be narrow enough to preserve views, but deep enough to reduce direct solar exposure. They also create a more articulated facade expression, making the environmental strategy visible from the outside. These visuals support the final design claim. The retrofit improves performance while still respecting the original glass tower identity. And the final page shows the overall architectural vision. The tower is presented as a retrofitted building rather than a completely new design. The proposal improves performance without full facade replacement. Vertical fins respond to Suzhou solar and glare conditions, while the existing curved tower form and curtain wall rhythm remain visible. The system is modular, reversible, and easier to maintain than a full recladding strategy. There are also limitations. The simulations are simplified. The exact existing glass specification is unknown. Structural verification would be required, and maintenance access would need further testing. However, as a facade theory proposal, the project demonstrates a clear, feasible strategy for transforming a static glass envelope into a layered environmental interface. The retrofit transforms the existing facade from a static glass envelope into a climate-responsive secondary skin, improving comfort and performance while retaining the building's curved architectural identity. To conclude, this project proposes a minimum intervention facade retrofit rather than full replacement. Through diagnosis, simulation, material strategy, technical detailing, and final visualization, the proposal demonstrates how an existing glazed office tower can be upgraded for solar control, comfort, life cycle performance, and architectural continuity. Thank you.